All right. So what we're going to do today is we're going to talk a little bit about, you should be able to guess the word by now. Efficiency, right? We're going to talk about efficiency. So I want to redo some things you've seen before, but from the perspective, how would we do them quickly? So let's go back to Pascal's triangle. So, I'm a huge fan of Pascal's triangle. It occurs in a lot of different things. We know the way of writing it is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, dot, 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 dot. You just write however many rows you need to fill up a lecture. Okay? Lots of nice properties. One of the nicest ones is each number is the sum of the one above and to the left plus the one above and to the right. And there's lots of different ways of proving this. From a computational point of view, there's a lot of great stuff here. We have a formula. We write n choose k, or if you're really old, you might write nck for the kth element in the nth row. And like all good mathematicians, how do you start counting? Zero. Right, when my son was very young, he learned that if I told him you can do something 3 more times, he would count 0, 1, 2, 3. Right? For those of you who program, you have to be very careful. Some environments start off with the first element of a list as the 0th element. Others start off with the first element of the list as the first element. There's good reasons for both. So we have a formula for n choose k. It is n factorial over k factorial n minus k factorial, where m factorial is m minus 1, 3 times 2 times 1. And we make the definition that 0 factorial equals 1. So the way of looking at m factorial is it's how many ways can I arrange m objects when order matters. I have m choices for the first, m minus 1 for the second, m minus 2 for the third, and so on. How many ways are there to arrange 2 objects? 2. 3 objects. 0 objects. 1. There's one way to do nothing. And if you think about it, well, I could do nothing this way or I could do nothing. No, right? You can't do nothing 2 different ways. And that's why there will never be another Seinfeld. Okay? There's one way to do nothing. Anybody even know Seinfeld anymore? All right, a few people.
Have you seen Mulaney?
I have not seen that.
I think it's coming out. He's essentially Seinfeld. Again, he's attempting to do Seinfeld.
All right. All right, in math. Hollywood is then outside my range of specialty.
I'm not saying it's going to work. It's
Okay, yeah. I think I can prove mathematically it won't work because 0 factorial equals 1. So the show will be a flop. Okay? Is it difficult theoretically to understand n choose k? Who has a calculator on them? All right. Could you calculate 100 factorial for me? All right. Does anybody else have a calculator that's readily accessible? Or a phone? Yes. Abacus. Calculate 100 factorial. The excitement is... It overflows. Okay, excellent. And this was not a planted question. All right. So your calculator cannot do 100 factorial. But let's say you really wanted to do 100 choose 39. There's a lot of ways to arrange the calculator. Yours did it. Okay. Do 1,000 factorial, please. I'm going to rumble.
Infinity.
All right. I will eventually look at what I am and am not allowed to ask students. If this is an inappropriate question, by all means, feel free to complain to the deans. How much did you pay for that? All right, yeah, keep meeting. Don't answer that question. All right, so I'm pretty sure 1,000 factorial is not plus infinity. Although for all practical purposes, plus infinity is not a bad approximation. Does anybody know how we could calculate 100 choose 39 on some of these calculators that are overflowing?
Really big Pascal's triangle.
One is really big Pascal's triangle, and some students who are quite concerned about their grades and willing to expand things out. Okay. I think even the Williams students at some point would just go to the dean's office on this one. How can I manage the calculation to avoid the overflow? See, I can't just plug in 100 factorial. Your calculator is not good enough. So one thing is store the previous row, but then how do I get, and these numbers could be quite huge, although they're not going to be too bad. And this is now going to be very intense in terms of storage costs. It's not a bad way to go, is to store the previous row and somehow get it like that. And so but that's essentially building up the whole Pascal's triangle. This allows me to talk or pontificate on a really important theme, the importance of doing a calculation in isolation or doing a bunch of similar calculations. So first, there is a good way to do this. This is 100 factorial over 39 factorial, and what do I have to multiply by? 61 factorial. So if you look at this, this is the same as 100 times 99 times 98. How far down do I go?
62.
To 62. And over here, I have 39 times 38 times 37 times 1. So one possibility is I just calculate the numerator and I just calculate the denominator. Depending on how large these things are, that will still be enough to overflow your calculator. But you can get a little bit further with that. What else could I do? Yes?
Could you do it by fractions?
Yeah, I could do it by fractions, and if I could somehow deal with the fractions and maybe some of the cancellations.
Yeah, you could eliminate like the numbers 1 through 33 on the bottom
by looking at
cutting out multiples of three.
by cutting out multiples of 3. And so there are lots of games I can play. And so in fact, all the stuff down here, up to the 31s, they occur 3 times. They'll have a huge power of 3 that I can pull out. So there are some tricks we can do to make the calculation more tractable. Okay? And this is an extremely important theme. Okay? Eventually, we will start really delving into linear programming and new methods. But I want to just spend the first week giving you time to review your linear algebra, because I'm not going to do that in class. Give you time to learn Mathematica or some other programming environment, and just try to teach you what this course is going to be about so you can figure out, I know some of you are still in flux, is this what you want to take? And some of you who've taken CS before, I really appreciate the fact that you are not sleeping right now. Okay? I know you've seen this many times, but I need to just emphasize how we can look at these calculations in a different manner and the advantages of doing that. There's another thing we can do. We can try to understand new values in terms of previous values. So let's say I know n choose k, and what do you think I want to calculate next? N choose k plus 1. So n choose k was n factorial over k factorial n minus k factorial. N choose k plus 1, bless you. Well, to calculate that, that's just going to be n factorial over k plus 1 factorial n minus k minus 1 factorial. Ah, that looks very similar to n choose k. And if I rewrite it, I can write this as n factorial over k factorial n minus k factorial. Well, I have a k plus 1. I only care about k. So I have an extra k plus 1 that I have to keep track of. Over here, I have an n minus k. I didn't have an n minus k. I had an n minus k minus 1. So I've actually put in an extra factor in the denominator. Am I allowed to do that? The fact that you're not saying no quickly means that I can do a lot in this class that I was afraid I wouldn't be able to do. Can I just put in an extra factor in the denominator? No. Okay. Sadly, doesn't matter that I'm the professor. I have to balance the books. And so if I put an extra n minus k down below, I have to put an n minus k up above. So I've multiplied by 1, one of my favorite things to do. And when I multiply by 1 like this, now I have my previous value, and I'm multiplying it by n minus k times k plus 1. And so now the answer is this is just n choose k, which is what we had, and this nice factor, n minus k over k plus 1. So if I know a value, I can calculate the next value just marching down like this. Do you think this is a good or a bad way to do the calculation? Do you think this is better than doing something like this where I have my fractions? Okay, so why is it better?
Because it allows you to build on what you previously have done, go back into the problem each time and figure out
squared if you
Okay, but this means I have to start all the way at, n choose 0 and work all the way up from that. So I'm walking quite far. So is it worthwhile to do that much walking? Yes.
Your factor is always smaller. The n minus k over k plus 1 is always smaller than n.
It is always smaller than n, so I'm controlling a little bit. But it's more than just the size of it. So it's this number has a very special property. It's a very special type of number. Not just this number here, but the whole thing. What kind of number is this? If you're Cam or Kayla, they only know this type of number. They don't know other types of numbers. It's a what? It's an integer, right? You don't have square root of 2 when you're 5 years old. Okay? The only things you have are numbers 0, 1, 2, 3. Maybe if you have a dad who pushes math on you, you might have negative numbers. Okay? But you're not going to have square roots of 2. Well, actually, we did do square root of 2. All right. Most people will not have square roots of 2. We did square roots of 2 with fuse beats. What's nice about this is an integer. The resulting multiplication is an integer. So what this means is k plus 1, does that have to divide n choose k? It doesn't quite have to divide n choose k. But if I multiply n choose k by n minus k first, then when I multiply by 1 over n plus, when I divide by k plus 1, I have to get an integer. So if I do it like this, I always stay with integers. If I do it like this and do 100 over 39 times 99 over 38, I could all of a sudden introduce round-off errors. And there are a lot of problems where stability matters. And so again, I really want you to adopt a new perspective. All right? This is probably the longest you will spend in your college career on a calculation that you most of the time will just type into a computer and the computer will solve for you. But there's a lot going on here that I think is really worth emphasizing if you haven't thought about these issues before. If you arrange the calculations in a different way, it fundamentally changes the computational aspect. It fundamentally changes how the computer works and how confident you can be on the answer. Are there round-off errors? And if you've done anything with chaos, butterfly flaps its wings and eventually there's a tornado in Kansas, this means you have to find which butterfly is going to flap now. So you want to worry about very small effects propagating quickly in the system. Small round-off errors could be multiplied enormously when you do something like this. This is a way to minimize stuff like that. So one of your homework problems is to actually calculate Pascal's triangle and see the Sierpinski triangle emerging from that. To do that well, you're going to need to do computational efficiency. Or you'll just give me a little plot with 4 or 5 rows, and that's not going to look that impressive. You want to see how far can you go. I can get up to about 2,000 rows without too much trouble on my computer. If you can get even 200 or 300, that's a good number. Enough to start to really see the fractal structure emerging. Okay, any other questions on Pascal's triangle here and just how we would compute stuff like this? Yes?
So this is useful if n choose k is a tractable number, whereas n factorial might not be. But this doesn't really help if n choose k is itself.
This is the fundamental idea here is some kind of recursive definition where you calculate the next term in terms of previous ones you understand. So for instance, n factorial, if you know n minus 1 factorial, n factorial is trivial. The problem is for some computations, n factorial can overflow your system, and you can't store it. And so you have to play all these tricks to keep things in memory. And this is a great way to keep things in memory. So please speak up and let me know what you're interested in about on this. Okay. Any other questions on this? Okay, so what I want to do is I want to take a little digression to dimension. And the reason I want to talk about dimension is it's tough to put up Pascal's triangle. We saw the video where you saw Sierpinski's triangle coming in. You saw this great fractal and not say anything about fractals. The other thing is I can show any movie that I can relate to my classes. So as long as I say something about fractals, that now gives us a little bit more flexibility in terms of what movies we can show at Williams. The other thing, and this one is the more important one for us, is a lot of problems, the dimension of the system controls the complexity, controls how difficult the calculation becomes. So we saw that naively when we did the sum of 1 plus 2 plus 3 all the way up to n, the naive approach was n squared. We then saw we could do much better. We saw we could do it how fast? So we could do it order n with Horner's algorithm and grouping. We looked at matrix multiplication. And naively, matrix multiplication was an n-cubed algorithm. We saw how to do it as n to the log of 7 base 2. And so what I want to do is I want to talk briefly about dimensions, because it is important for so many problems. So dimensions. What's the dimension? I'm sorry? 2. You are correct, but if I had better chalk, and Professor Devados has a beautiful blog post on the department homepage on this chalk from Japan, the magic chalk. There's some people who swear by this. Even that chalk sadly would not be sufficient for this. This is a two-dimensional object, but really what is it supposed to be? It's supposed to be one dimension. 2, 3. Yeah, I don't even have to draw it. You know it's 3. It's really good that I don't have to draw things anymore because I'm going to have trouble after that. Okay? So I want to try to come up with a notion of dimension. I think we all agree 1, 2, 3. How many of you have ever seen the movie Flatland? Actually, pretty good movie. And they try to talk about, it's about a world of 2 dimensions. What's nice is we can imagine the 3-dimension very easily, but the people in Flatland who live on a plane, to them they cannot imagine. The sequel tries to do 4 dimensions. And it's a visually interesting challenge. So here is a definition of dimension. Say dilate a set S by a factor of R and get C copies of S. Then the dimension D is, or satisfies, R to the D equals C. All right, so here's an interesting formula. This is the Hausdorf dimension, essentially. So how many of you have seen a definition like this before? Excellent. Finally found something that people have not seen, or at least not publicly admitting. What should you do whenever you get a new definition? What should you do? Think about it. So how could we think about it? What could we look at? I'm sorry? Some examples. Any particular examples you could think of? I'm sorry? No. Let's start easy. Walk before you run. What would be good examples to think of?
What the word dilate means in this context.
What the word dilate. So it means basically expand by a factor of R. So if you take a set, let's say it's a set centered at the origin, I multiply everything by R, so I stretch everything by a factor of R. Yes?
I mean, you could just try the things that we already know.
Yeah, there might be a reason why those things were written on the board. Right? Foreshadowing. Right? Here are some examples where you know what dimension means. Here is a new definition of dimension. Let's see, how does that relate to the notion of dimension we understand? So if I take a line and I multiply by a factor of R, how many copies do we have? R copies. Have R copies. So C equals R to what power? 1. Therefore, D equals 1. So a line has dimension 1. Yes?
What do we mean by R copies?
So, for instance, if I equals 2, we go from this, say, 0 to 1. I now multiply by a factor of 2, and now I have 2 copies of my interval. If I take R equals 3, here's 0, 1, 0, 1, 2, 3. And I now have 3 exact copies of what I started with. And so we can see here very clearly that it's going to look like D equals 1. For these arguments to really work, R should be what kind of number? Integer. Okay, so now for another example, let's do the 2 dimensions. And let's take R equals 3. How many copies? So copies equals 9. 9 is 3 squared. The square is a 2-dimensional object. What do you think is going to happen if we try a cube? The dimension of the cube will be 3. If I drew the hypercube, which would be really impressive drawing a 4-dimensional object on a 2-dimensional surface, but what would we get for the dimension there? The hypercube, which is really happy to be in class today, it would be 5, and so on, right? So you might, instead of saying hypercube, because this is really sounding childish, you might just say the dimension of the cube. You know, the 5-dimensional cube has dimension. Well, the name is really saying it all there. It's not too surprising. All right, so the reason why we like this notion of dimension is it allows us to handle cases we won't have before. So we have the Sierpinski triangle. And this was the fractal shape we got. And so what we basically do, and I'm only going to do it finally often, is we throw away the middle region. And then we keep iterating this process. I now have 3 triangles, and I throw away the middle of each one of them. And now what do I do? No, the Cantor set is essentially a 1-dimensional analog of this. And so one of your homework problems is actually going to be calculate the dimension of the Cantor set. And so here, I now throw away the middle parts of all of these triangles. If Williams loved you, I would have colored chalk, and you would see all the different cuts in different colors, but that's fine. All right. I think I've now filled in enough material that I can finish off the lecture and not end too soon. All right? So the process just continues. What you'll notice is this part over here is the exact same as this part over here, is the exact same as this part over here. So there are 2 ways to go. I could maybe inflate the triangle by a factor of 2, or I could decrease the sides of the triangle by a factor of 2. I would rather increase and get more copies. It doesn't really matter. If I now multiply everything by a factor of 2, so I stretch everything by a factor of 2, let's think of what goes on. This whole thing over here, this part over here, when I multiply by a factor of 2, this was initially maybe 1 unit long. Now this is 2 units long. This small part over here now comes into over here. Did I do it times? No. I think that's the number, the love percentage. Blah. So this part over here goes to this part over here, right? I have nothing down here in this big region. This triangle here, or that region over here, comes down into here. This region over here comes down to here. How many copies of my original set do I have? 3. So number of copies is 3. And what does R equal? What's my dilation factor? 2. So therefore, copies is R to the D. So copies, so 3 is equal to 2 to the D. How do we solve this? Logarithms, log base 2. The log base 2 of 3 is equal to D. If you are a computer scientist, how many of you are computer scientists? Would you actually put the subscript 2 in computer science? Not usually. In computer science, when you write log, you mean log base 2. Because in computer science, the computers are built on logs, so they're built on binary. In a math class, if you don't put a subscript 2, what do we think? E. We think base E, the natural log. Okay? Is this answer reasonable? So this is D is approximately, I think, 1.58. I wrote this down, yes, about 1.58. Is that answer reasonable? So whenever you calculate something, you want to say, is it reasonable? Where does 1.58 live between? Between what numbers? 1 and 2. So 1 is less than D is less than 2. Does it make sense that the dimension of the Sierpinski triangle is greater than 1? Yeah, I mean, I kind of see lines in here. The lines have dimension 1. It's more than a line. It should be more than one dimension. Does it make sense that it's less than 2 dimensions? Yeah, it's missing a lot of parts to it. So the idea that its dimension is somewhere between 1 and 2 sounds reasonable. The fact that it's a little bit closer to 2 than 1, I'm not going to go there. But this kind of relation that, yeah, it should be somewhere between 1 and 2, that's not so bad. Okay, so again, this can be extremely important to get some idea of how complex your system is. And just so that you're comfortable with calculations like this, I will have you do the Cantor set. And so for the Cantor set, you will be able to find this calculation, of course, online. If you just type it in, try to do it on your own first. I will just define the Cantor set quickly. Cantor set. So throw away the middle thirds. So you start with the interval 0, 1. You then throw away the middle third. So here's 1/3 and 2/3. You throw this away. And now you throw away the middle third here. So that's 1/9 to 2/9. You throw that away. 7/9 to 8/9. You throw that away. And you keep iterating. And you see what's left over. What should the dimension of this be? Where should it live between? It should live between 0 and 0 and 1. Okay, so you'll just calculate this. What base do you think will matter when you do the logarithm calculation? So which base? I heard 3, I heard 2. I heard 1. R. So when R is your dilation factor. So you've got to figure out what do you want to dilate by to get basically copies of things again. So here we saw if we doubled the triangle, then this filled in very nicely. So you want to figure out what do you need to do to get that to work nicely there as well. Okay. Any other questions on the Sierpinski triangle or on the Cantor set? Okay. So this gives us now the opportunity to talk a little bit about logarithms. How many of you have seen logarithms before? This is essentially the who is awake right now. At this point, you should have all seen logarithms. All right. How many of you can prove all the different log laws? How many of you can name the 7 dwarfs? All right. Which is the dwarf that's most forgotten? Sorry? No, he's the leader, and people love professors. People remember Doc. He's even in my office. Bashful. Typically, Bashful is the dwarf that is most forgotten. Okay? If you are comfortable doing so, but if that would embarrass you, then by all means don't email me about Bashful. Yes? Was there? I think this is a scientific fact. I think extensive surveys funded by the National Science Foundation and other institutes have determined conclusively that Bashful is the most forgotten of the dwarfs. I actually sometimes combine 2 of the dwarfs when I do things together, and you can figure out how I combine them. So, all right. What are the log laws? What's the first log law? So I guess the log of x base b equals y, this is the same as x equals b to the y. What's the first log law? All right, so we'll do log of x1 plus the log base b of x2 is the log base b of x1, x2. The log of a product is the sum of the logs. This is why anybody who's taken a class with me knows why I love taking logarithms of products. Because logarithms of products become sums. We know how to do sums, or at least we're more trained in that. And so again, a huge part of this course is figuring out the right way to look at things. Taking logarithms converts products to sums. This is extremely useful. Okay? Another one which people often isolate is the log base b of x to the r is r the log base b of x. Okay, another one? Yes?
E to the natural, I guess b to the log base b of x is x.
Okay, b to the log of x base b equals 1. This is proof by words. I take b and I raise b by the number of powers of b I need to get, I need to get x, and I get x. All right, there's another log law which is related to one of the ones above. Yes?
Division is subtraction.
Division is subtraction. Excellent. The log base b of x1 minus the log base b of x2 is the log base b of x1 over x2. Really, to me, this is really log laws 1 and log law 2. Because if I just take these together, if I just take I equals -1, I get this. Yes?
The change of base.
Yes.
Log base b of a is log base anything of a over log base anything of b.
And they're the same anythings, right? They're the same anythings.
Yeah.
Yes. So change of basis. So to me, this is the bashful of the log laws. And I don't think it's a coincidence that it starts off the same as bashful. Although I cannot prove that. All right. The change of basis is, I think, the most forgotten of the log laws. Okay? So if you want to prove the log laws, the proofs are not so bad. So I'll just prove one of them. Proofs. So proof of 1. So the log base b of xi equals yi. That implies xi equals b to the yi. So x1 times x2 is b to the y1, b to the y2. So how many powers of b do I have? y1 plus y2. But now by definition, I get the log base b of x1, x2 is y1 plus y2. But that's just then the log base b of x1 plus the log base b of x2. So that's the proof of one of the log laws. The other log laws are proved similarly. It's going back to the definition, interpreting what you're doing. The change of basis is a little bit more fun as to why is this true. Which log law do you think is the most important? And do you think the importance is independent or dependent on what year you're talking about?
5 is most important for anything before calculators.
I'm sorry? 5 is the most important before calculators. And the reason this is the most important is it allows you to calculate logarithms in any base so long as you know logarithms in one base. There are people whose job used to be tabulating values of functions. And I'm trying to imagine, any Seinfeld fans here? Okay, episode 701, 7th season, first episode, The Engagement, when Kramer's describing what it's like to get married, and you come home, how was your day? Was it a good day? Was it a bad day? What kind of day did you have? And then he just goes on as to, I'm trying to imagine what it would be like to go home. So what did you do today? Oh, I calculated 15 more logarithms to 7 decimal places. And what are your plans for tomorrow? Calculate 15 more logarithms to 7 decimal places. And the next day, 15, and this is what people did. They used to tabulate values of functions. There are massive books on this. There are books on tables of primes. These things were jobs. There are people who calculated digits of pi. And there are people who checked people whose work who calculated digits of pi. And to me, this is extremely boring. Why is this so important? If I can calculate logarithms in one base, I can get them in any base. Which base is the most important base to use? So if we want to do derivatives, e is the most important base. But if we're not doing derivatives, if we're actually looking at data, we may not want to do things base e. What base might we want to use? 10. We have 10 fingers. There could be some things for scientific purposes, maybe for biology, where we care about populations doubling. Maybe base 2 is the natural base to use. And the whole point of 5 is you only need to calculate logarithms once in one base, and then you get all the other bases for free. So there is a name for this. It's called a, anybody know what this is called? When you calculate all the values of a function, you create a, I think I heard somebody saying it begins with an L. A lookup table. This is one of the most important things you can do. It's pre-computing results. From a theoretical point of view, does this matter? No. At some point in the semester, I will stop doing this, and I will assume that everybody has been convinced that this is a class worth taking. As some people are still auditing, I will continue to try to emphasize for just a little bit longer. So, lookup tables. I have not checked if the following story is true because I really like the story and I hope it's true. And so I am not checking it, but many years ago when I was teaching at Brown, some of my students did a project on ancient mathematics. And they told me the following story. How many of you know anything about Babylonian mathematics? Okay. What did we inherit from the Babylonians? Yes?
Base 60.
Base 60. 60 seconds in a minute. 60 minutes in an hour. Now, we actually have almost 360 days in a year, so that actually worked out really nicely. Moon cycles, about a month, about 30. 60 has a lot of nice factorizations, which is wonderful. 360 degrees in a circle. So we've inherited. All right. Who knows their multiplication through the 5s? If I give you 4 times 3, can you bat it out? All right, multiplication through the 10s. 11s. 11s aren't too bad. You should have your hand. If you can do 10s, you can do 11s, right? 7 times 11, 8 times 11. The only one you have to think about for a second is 11 times 11. All right, 12s, 13s, 17s. Yeah, okay, so somewhere between 13 and 17, everybody drops off, and you've no longer memorized. So what do you do, especially if you have some of these weak-ass calculators that can't do these great computations? What do you do if you have to do 16 times 17? I'm sorry?
I said you could break it into smaller.
You could break it up into small things that you know, and then you can combine. Okay, so in some sense, you have almost like a lookup table in your mind. You have the multiplication through 10s, and then by using that and using a good process, you can take that information and do these more complex operations. Imagine you're an ancient Babylonian student. So you're going to do this process as well, but now, how much do you have to memorize? A lot. Let's quantify a lot. 60. All right, so for the poor Babylonians, 60 by 60 is how much? So that's how many multiplications you have to memorize. Can we help out the ancient Babbies? Yes. Cut it in half. Almost. You can't quite do it in half, but you can do big savings. It's 60 times, it's actually 60 choose 2. 60 times 59 over 2. If you want, it's 3,600. Subtract off all the x times x, divide by 2, and then add the x by x's back. So approximately 1,800. All right, it's still bad, but it's a lot better. And this is an example where saving a factor of 2 would be useful. Will the Babylonian children memorize 1,800 multiplications? No, they've got other things to do. Life was not easy back then. You cannot spend this much time memorizing. So what would they do? Yes? Write them down. Great. So they would just take like a piece of paper and a pen and just write it down. or just store it on their phone, what would they do? This is Williams. This is a liberal arts institution. Some of you should have some knowledge of history. Yes?
They have clay tablets.
Clay tablets, right? So yes, you will get some exercise carrying around clay tablets, but you're not going to want to lug around too many clay tablets. So this is one of the greatest ideas I've seen in my life as to how the Babylonians, and again, I haven't checked to see if this is true, the way you can multiply x times y is x plus y squared minus x squared minus y squared divided by 2. From a theoretical point of view, good thing or bad thing to do? Bad. Right? I've taken one multiplication and I've exchanged it for 3 multiplications, 2 subtractions, a division, and a partridge. Okay. This is a bad trade-off. Right? Why might this be a good thing to do? Yes. Yeah. Yes.
Because it's squares.
It's squares. So now I only have to have a lookup table of squares. How many things do I have to learn now? On the order of 60. Learn 60 items. That is far more manageable than 1800. And so in terms of bringing things on tablets, it's a lot less. Now I have to do subtraction. The subtraction is a pain, but it's not so bad. I have to do a division by 2 at the end, a pain, but not so bad. And so to me, this is a wonderful example of the trade-offs that happen in life. Okay? And then, again, if you're going to do anything, you want to really think about what do you want to pre-compute. Question? Or was there a question? Or yes, go for it. So you might have to do 120 items because you've got to get all the way up to things squares. So learn approximately 60. That could be 120. So I would definitely accept learning 120. Now the ancient Babylonian students, if you tell them they only have to learn 60 and they now have to learn 120, they'll be upset. So you've got to be very careful when you sell this to them that you give them the right number first. Much better to go down than to add things later. Oh no, you're not done yet. You've got to learn another. Yes, I think you're right that you have to learn 120. But this is absolutely wonderful in terms of what it saves. Now, there's a problem with something like this. This only works for certain types of multiplications. If I want to multiply, 53 by 13, I can do that. What if I want to multiply 53.5 by 13.4? I don't have that now. So what you need is you need more than just a lookup table. You need a process which is called interpolation. If you have a couple of values in a lookup table, how would you determine values of nearby related quantities? And so some of your homework problem is to actually do this, either for like trig tables or for tables of values of areas under the standard normal. These are problems that are very, very important. And I want you to get a sense of how would you use these lookup tables to handle analyses like this. So again, in general, you're not able to pre-compute everything, but you can pre-compute a lot of things. And then if you have some process that allows you to take those pre-computed values and build things from them, it's great. Okay? So, if somebody wants to look up this and tell me if it's true or not, that would be good to know. I haven't really brought myself to go to Snoops. The following story, which some of my Calc 3 students may have heard, is almost surely false, about another example where it's a wonderful story, but this one I don't think is true. A company was trying to build a stealth fighter or a stealth bomber. What do you want to do if you're building a stealth plane?
Not tell anyone.
That's part of it. What property do you want the plane to have? What are you trying to do? You want it to be quiet. You want to minimize detectability. You want to maximize stealthiness, something along those lines. And so the story is that people were trying to maximize stealthiness, and they did this as a calculus problem. They took the derivative, they set the derivative to 0, and what did they forget to do? Yes, check to see if it's a maximum or minimum. And the story goes that they actually had the minimum, and that they should have realized that the clown horns and the flashing signs should have been a dead giveaway. No, so okay, almost surely the story is false that you're not going to build the show me plane. But you want to be very careful in stuff like this and make sure you're doing the right calculation. For a lot of things, it is clear if you're going to have a maximum or a minimum. And you don't have to worry. You can often make arguments from physical grounds. So for this problem, it doesn't really matter. It doesn't really matter if the story is true or not. This is still a beautiful idea, and you can see the enormous savings in going from on the order of 120 objects to 1,800 objects. Okay? So I think this is going to end, for the most part, I think, the introduction to computational mathematics and the ways of looking at things. And then we're not going to have class on Friday, I believe. I will send out more details as to what's going to happen. But then on Monday, we will go in full force and start going through the chapter on linear programming. So you have plenty of time now to play with Mathematica, stuff like that. Make sure you're confident with your abilities to program. If you have questions, talk to me, talk to your classmates.